Hello. It seems you want to learn a little about temperature. I was just about to go over the basics with Martha, so you picked a good time to drop in.
It's Marcia.
Well, Martha,
Marcia.
let's start with a simplified description of temperature, and then add in some details once we've mastered the basics. First, let me ask you, do you know what kinetic energy is?
Sure. Kinetic energy is the energy of motion. An object with kinetic energy is moving.
Right. For example, a car driving down a highway has kinetic energy.
And we calculate the car's kinetic energy as half of its mass times the square of its speed. Right?
Exactly. Now, as we continue our discussion, we'll talk not of cars but of gas particles, because it's a lot easier to discuss temperature in terms of an ideal gas.
The ideal gas is free and doesn't pollute when it burns. Am I right?
What? Is that a joke? No, I'm talking about gas like the helium in a balloon. What makes a gas ideal is that the gas particles are tiny, infinitely small actually, and they don't influence one another except for when they collide, which they do quite frequently. Gases in the real world are typically not ideal, but that doesn't prevent us from discussing them.
Speaking of the real world, I sometimes think that we're not real. You know, like we are a simulation in the computer of a higher power, like in that movie The Matrix.
Don't be silly, Martha. Of course we are real, just like the 10 to the 23 atoms or molecules in a mole of gas, zipping around at enormous speeds.
I think I know where you're going with this. Those atoms or molecules have kinetic energy.
Yes, they do. If you have a container filled with a mole of ideal gas, each of those gas particles has a tiny bit of kinetic energy. I say tiny because, even though each particle is moving rapidly, each has an extremely small mass. However, if you add up the kinetic energies of all the particles in the container, you end up with a relatively large amount of kinetic energy, called the internal kinetic energy of the gas. The temperature of the gas is a number that is proportional to the internal kinetic energy, as well as the average kinetic energy of a single particle.
So the particles in a high-temperature gas move, on the average, faster than the particles in a low-temperature gas.
That's right. The faster they zip around, the greater their kinetic energies, and the higher the temperature of the gas.
So for a given temperature, do all the particles move around at the same speed?
Who are you? When did you get here?
I think you know who I am, and I arrived just a moment ago.
My dad loves you.
And I love your dad.
Wait. What?
I love Steve, your dad.
How did you know his name?
I'm just kidding. So what about my question?
It's a good question. Sorry, it's really strange that you're here. Okay, well, in the collection of gas particles, almost no particle actually moves at the average speed. Particles move faster and slower, some much faster or slower. In fact, if the gas has reached a state of thermal equilibrium, the speeds of the particles are always distributed a very special way. It's called a Maxwell-Boltzmann distribution. Looks sort of like a bell curve. Most particles have speeds centered around the average speed, and you find fewer and fewer particles at speeds farther and farther from the average, in both directions.
And this is true for any temperature? Seems like at really low temperatures, corresponding to low particle speeds, the Maxwell distribution doesn't have much room to spread out on the side of lower speeds.
Good point. As the gas gets colder, the distribution gets narrower and taller. It approaches a spike.
So really cold gases have very little spread in particle speeds?
Exactly. Imagine that all the particles in a container were moving at the same speed, say, 1,000 miles per hour. If we were to switch reference frames, so that we were moving 1,000 miles per hour alongside the particles, we'd observe all of the particles to have a speed of 0. With no kinetic energy, they would be as cold as is possible. They would have a temperature of absolute 0. A temperature is associated with a spread in particle speeds.
What if you have just a single gas particle? There can't be any spread in speeds if you have just one particle.
That's right, so a single particle doesn't have a temperature. Temperature is a characteristic of a gas as a whole. It has no meaning for single particles.
Absolute 0. Isn't that the same as -273 degrees Celsius?
That's right. or just 0 on the Kelvin scale. Nothing in the universe can be colder than absolute 0 or 0 Kelvin. Actually, nothing can have a temperature of absolute 0 itself, although scientists have managed to cool things off to billionths of a degree above it. Interestingly, it is possible to have a negative temperature on the Kelvin scale.
No sens. Oh, quand you have a negative temperature, you just say a few seconds ago that nothing could be cold at absolute 0.
What?
He said, nonsense. How can you have a negative temperature if nothing can be colder than absolute 0?
Am I hallucinating? Wait. You speak cardboard box.
I speak French. And the box has a point. A point. Get it?
Well, a negative temperature on the Kelvin scale is not colder than absolute 0. Strangely, negative temperatures correspond to extremely hot gases. Hotter than a gas at any positive temperature.
If I may direct the audience to the comments below the video, there is a link to an article on this very topic.
So now I know the definition of temperature. It's related to the average kinetic energies of the particles of the gas, or whatever object we're analyzing. Hotter gases have faster moving particles. And it's also related to the spread in speeds about the average particle speed. Hotter gases have a greater spread in speeds.
True, but I haven't given you the exact definition of temperature. It's actually defined in terms of entropy, a topic we'll save for a future discussion.
Sounds good. Wait. How did you know my dad's name was Steve?